What's up, guys? Mr. Rushka here. Just started a 45-minute stopwatch. All right, so actually I should probably make that a 45-minute timer. All right, just started a 45-minute timer. All right, so I'm just going to start lecturing, starting from where we left off today. I'm just going to see how far I get in 45 minutes, and then that's what I'm going to have you guys watching class tomorrow, all right? So today we left off at this first box problem here. Okay, so let's start the second box problem, okay? I'm actually glad these are on separate days so we can review, okay? So we're going to repeat number one for a 21-inch by 16-inch piece of paper again. So, right, we're going to have a square box, or a rectangular box, I should say. The sides are not the same length, so it's not a square. So this length right here is 21 inches, and my width is 16 inches, okay? All right, and then we're going to cut some sort of a square box out of the corner and then fold up these corners to make a box, right? So we have this paper. We're going to cut the corners out, cut squares out of the corners, okay? And then we're going to fold them up to make it into a cardboard box, okay? So how far we cut into the paper actually isn't specified. So we're going to cut X units into the paper, and since these pink squares, since they're all squares, all the sides are the same length, so we're all gonna have, all these cuts are gonna be length X, okay? All right, so let's come up with a function for the volume of this future box, I guess. So, right, volume of a rectangular prism, volume of our box is gonna be length times width times height. Length times width times height. Okay. All right, that's going to be the volume of our box, okay? So let's think about this, okay? Let's think, let me highlight this in green. What's the length? What's the length of my box going to be, right? What's the length of my box going to be? Well, the length of the paper is 21 inches, okay? Right, so that you might think, okay, the length of the box is going to be 21 inches. Well, not quite, because what we're doing here is we're cutting X inches into the length of the paper from both sides. So we're taking an X out of the length here and another X out of the length here. So we're starting with 21 in our length, and then we're taking away from that 2 times X. Okay, so that's going to be the length of our box, okay? Let's talk about the width of our box, okay? Okay, the width of our box is going to be the same thing, okay? We start with 16 inches. We start with 16 inches of width. Right, but we are going to cut into the box from the side, and we're going to take away a length X from here and another length X from over here when we cut into the box, into the corners, okay? So we got to take away from our 16 a 2X, okay? All right, and let's talk about the height. The height of our box. The height of our box, right? So when we fold the corners up, I wish I had like a model for this. When we fold the corners up, right, the height is going to go from here, this corner of the square, all the way to the edge, of what's going to be the box of this paper, okay? So the height is going to be length X, is going to be the height. That one you just kind of got to visualize. So that's going to be our volume, okay? So X is a variable, so we're going to write V as V of X, because V is a function of X. This means that V changes as X changes, right? Our volume depends on how far we cut into the box, okay? So here's our, I'll just like underline. Let me circle this, okay? Oh, whoops. So circle this, okay? So this is our big volume function we're looking at for this problem, okay? So let's think about the domain of this function, okay? So if we were to graph this on a graphing calculator, the graph itself that the calculator is going to pull up is going to be, it's going to look like the domain is all reals, okay? And that would be true. This function, if we weren't thinking about it in the context of this problem, this function does have an infinite domain. The domain is all reals, okay? That's what your calculator is going to be thinking, right? What your calculator doesn't know is we're actually just trying to use this function to model the volume of a real-life box in real life, okay? So just like we talked about in class yesterday, right? we got to think about constraints and how far we can cut into the box, and that's where our actual domain for this problem is going to come from, okay? So let's think about the lower bound for x, okay? The lower bound for x would be 0, okay? Right, that's because of x, we can't cut negative, right? We can't cut a negative length out of this box. What does it mean to cut like negative 2 inches into something? That's like not even, statement doesn't even have meaning, okay? I'm gonna give it some water. All right, so we can't cut a negative x out of our box. We're also not gonna cut 0. Right? Our cut can't be of length 0 because then that wouldn't be a cut. We wouldn't have a box, we just have a piece of paper. So our cut has to be positive, so it can't be negative or 0. So I'm going to write 0 with a parenthesis. Okay? Right? And then the farthest I can cut into my box, is 8 inches. Okay? I can't cut 8 inches either, okay? Because my width, you take what we did here is we took the shorter dimension of our box, so 16, okay? And we divided it by 2, and that became the upper bound for our domain. That's because if my cut becomes 8 inches or greater, I don't have squares here anymore. I literally just cut the paper into 4 pieces. So I'm not going to have a box. That would mean I just cut these huge strips, right? So these wouldn't be square corners anymore if my cut were 8 inches, because that would mean I just sliced these 2 edges off. Wouldn't have a box anymore. Okay, so that's going to be my domain right here is going to be parentheses 0, 8 parentheses. Okay. All right, max volume. Here's how we find this, okay? So let's plug. Let me write this function down on a paper real quick so I can remember what to put in my calculator. There we go, okay? So what we're going to do is we're going to go ahead and take this function, v of x, and graph it in my calculator. So good news, I finally got calculate 84 on my iPad, long time coming, okay? So we're going to do 21. I'm going to hit the y equals button right here, okay? 21 minus 2x times 16 minus 2x times x, okay? Let's hit graph, okay? So what we've got here, right, we can't really see anything much of interest. We can't really use this. We're looking for a maximum, so we're looking for a peak on this graph. So let's just start out with doing a zoom fit, hitting zoom fit. All right, this is great. This is money right here, all right? So we're going to look at x going between, oh no, hit zoom fit again. There we go. We want to look at x going between 0 and 8, because that's our domain. Remember, our domain was 0 to 8, so we're only interested in this region of the graph because the x's that are bigger than that or smaller than that don't really make sense in the context of our problem, right? We wouldn't really have a box anymore. So we want to see what the v or the y value is at our peak on this little hump here. This little hump peaks out about right here. And if we use the second calc button on our calculator, it'll actually tell us the exact x and y value on this hump where this hump reaches its maximum height or its maximum volume in the context of this problem. Okay, so let's go to the left of the hump. All right, so let's hit the second button, then calc. Hit maximum. Okay, my left bound, let's do like right, let's do like right here for my left bound. You see this little thing I'm moving around here? We're gonna put our left bound to the left of our peak, okay? Hit enter, it's gonna give us a right bound line. We're gonna drag that to the right of our peak, so over here. Okay, hit enter, and then it gives us that y value in blue, 352. See, I'm looking at the bottom left corner of the screen. y1 equals 352.26, okay? 352.26. And that's going to be inches cubed, cubic inches. It's going to be our max volume. We just did that with our calculator, okay? All right. So what this next part is asking us is what are the size of the corners? How far into the paper do we cut to get this max volume? Okay, well that would be the x value that gives us our maximum, okay? So if we cut look at the bottom left corner of my screen now, if we cut 4.78 inches into my paper, right, that's going to give us a box. This cut is going to give us a box with this maximum volume here, okay? So that's how that's going to work, okay? There we go. So pause, ask Mr. Miller for help if you're confused. All right. Just play it slowly, rewind if you need to, okay? Number 3, a jumper that normally costs $11.50 is on sale for 30% off. Sales tax is 7%. What's the final cost of the jumper? Okay, here's what's going on here, okay? So we're taking our, how do I want to explain this one? So we're going to take our jumper, right? At first, our jumper costs 100% of the original price, okay? 100% of the original price is just the original price, right? That's just the original price, okay? So we're going to take off of that 100% our 30% off. That's going to give us 70%. Okay, that's going to give us 70%. All right. Okay. So 70% of our original price is going to be our sales price. Okay, so we're going to do 70% of 1150 is 1150 times 0.7. That gives me 805. So the sale price is going to be $8.05, right? That's going to be my sale price, okay? But we've got to add on to our sale price the sales tax, okay? So sales tax is 7%. So our sales tax takes our new price right here and it adds on 7%. So 100% of our what we just paid at the register plus our 7%, right? That equals 107%. Okay? So to get the actual price we pay, the final cost, we have to do $8.05 times 1.07. Okay? So I do that in my calculator. All right, 805 times 1.07. That gives me, rounded to the nearest cent, to the nearest hundredth, that gives me $8.61. Okay. That's going to be my final answer right here. I'll circle it. Final answer, $8.61. Okay. So go ahead. All right. Pause, screenshot, whatever you need to do, okay? Now we want to repeat number 3 now, okay? Repeat number 3, okay? So we're going to do, we have a shirt that's $16.95 to start off with, okay? We're 18% off, right? So 100 minus 18 equals 82. All right. So our shirt is only going to ring up at the register for 82% of the original. So the original cost right here is 16.95. If we multiply that by 0.82, we get $13.90. That's rounding to the nearest hundredth. So the register is going to ring up $13.90, and then it's going to apply our 5.5% tax to this cost right here. Okay, so we take 100% of $13.90, we add on to it our 5.5%. That's going to give us 105.5%. Okay. All right. So 1 plus 0.055, right? That is 1.055. Okay. So we have 1390 times 1.055. Okay. That's going to give us $14.66 as the final cost that gets rung up at the register, okay? So to recap, we took our original price, multiplied it by 82, by 0.82, because we actually want 82% of the original price, okay, because we get 18% off. That gives us what we ring up at the register. The register is going to add in the tax, okay, so we multiply $13.90 by 1.055 since we have an additional 5.5% on top of our sale price to pay, okay? So 105.5% of $13.90 is $13.90 times 1.055. That gives me my final cost of $14.66, okay? All right, so for this next part, right, I'm doing all these textbook problems, okay? So this is textbook page 160. So you should hopefully have the textbook problems still on you, okay? So we're gonna go to page 160 here. Okay, it says quick review 1.7 at the top right here. It says quick review 1.7. We're gonna do 15, 16, 17, 18, 19, 20. So I'm circling these. And on 161, we're gonna do 32, 35, 37, 38, and 39, okay? All right, so I'm going to start with number 15 here, okay? Right, so the height of a right circular cylinder equals its diameter. Write the volume of the cylinder as a function of its radius, okay? So let's go back to our notes. Okay, so number 15. So for these geometry type problems, I like to draw a picture. So right circular cylinder. There we go. All right. So we have a radius here. We have the height h, the radius r, and then the diameter d would be 2r, okay? Okay. What does the problem say? The problem says, so I'm looking at the packet. The height equals the diameter. So h equals d, or h equals 2r. Okay. H equals 2r. They want us to write the volume of the cylinder as a function of its radius. So the volume of a cylinder in general is going to be pi r squared h, okay? So pi times r squared times h, okay? As a function of radius means they want us to eliminate this variable h. So how do we do that? We substitute in our 2r here for h. So we have h here, we're just going to substitute in our 2r here. So that's going to give me v, I'm going to write v of r equals pi r squared times 2r, which equals 2 pi r cubed. 2 pi r cubed. All right. So writing the parentheses r means v of r, and it just specifies explicitly to the reader like, hey, volume changes if my radius changes, right? Okay, that's just saying the size of my cylinder changes if I change its radius, okay? So there's number 15. Let's go to look at number 16. Oh, whoops. Let's go look at number 16, okay? One leg of a right triangle is twice as long as the other. Right, write the length of the hypotenuse as a function of the length of the shorter leg, okay? As a function of the length of the shorter legs. Okay, so the variable that we're a function of is usually x, okay? So let's draw a little picture. So we have a right triangle. One leg is twice the length of the other one, so that's about that, okay? All right, then write the length of the hypotenuse as a function of the length of the shorter leg. As a function of the length of the shorter leg. So we're just going to call the length of the shorter leg, we're going to call it a length of x, since that's what we want to be the variable that we plug into our function. Okay, and then, so the other leg is twice as long. It's twice as long as this, right? So twice of the length of the short leg is twice of x, so the longer leg of the triangle is going to have length 2x. Okay? And then we got to write the length of the hypotenuse, h, right? Right? That's just Pythagorean theorem, right? So we have h squared, the length of the hypotenuse, is going to be equal to 2x squared plus x squared, okay? All right. So we want the length of the hypotenuse as a function of x. We almost have, that means we got to get h by itself, okay? We want to get h by itself. We almost have it by itself. We just got to get rid of this squared exponent here, so we take the square root of both sides, okay? So I have h equals plus or minus the square root of 2x squared, 2x in parentheses squared plus x squared, okay? Here's what I do with this, okay? So first of all, we have a positive square root and a negative square root. We're only going to keep the positive one. Why? So we get rid of the negative one. We only keep the positive square root because the length of our hypotenuse can't be negative. So we're not going to keep the negative square root because hypotenuse can't have negative length. And then let's just simplify with our algebra in here, right? That becomes square root of 4x squared plus x squared, which equals the square root of 5x squared, which equals x root 5, okay? So h of x is equal to x root 5, okay? So pause if you need to. We're just going to keep going, okay? You can always pause and rewind and slow down on your own if you need to. All right, let's go back. Number 17. The base of an isosceles triangle is half as long as the two equal sides. Right, the area of the triangle is a function of the length of the base. All right, so let's go back to our notes packet here. I'm going to get rid of this right here. So we're going to do number 17. Okay, so we have an isosceles triangle. Okay, so these two sides are congruent. Okay, these two angles are congruent. Okay. And we're saying the base is half as long as the two equal sides. So we want to write the area as a function of the base. Function of the base, I'm going to write the base. The length of the base is x. Then the length of these two sides is 2x. Okay. We want to write the area of the triangle. So in general, the area of a triangle is 1/2 base times height. Okay. My base is equal to x because that's what we just started with. My base equals x, okay? We got to figure out what the height is in terms of x, okay? We got to figure out what the height is. So that's going to be this pink dashed line right here is going to be the height, okay? So let's zoom in on this right. This is our height forms a right triangle with the base. So let's just zoom in on just this right triangle on the right. So we're going to have a right triangle whose base, right, what's the base of this right triangle? It's going to be, right, it's going to be, so this pink dashed line splits our base into 2 halves. So the base of this pink right triangle is going to be 1/2 of x. Its height is going to be h, and its hypotenuse is going to be 2x, right? So we can relate these three sides with the Pythagorean theorem, right? Because the square of the first leg plus the square of the second leg has to equal the hypotenuse squared. All right? So we relate them with the Pythagorean theorem, and then we can solve this for h to get an explicit formula for h that we can plug into our area formula, okay? So let's do this. 1/2 x squared is 1/4 x squared. So h squared equals, and then 2x quantity squared is 4x squared. Okay, let's subtract 1/4 x squared from both sides. H squared equals, what's 4 minus a 4th? Let me use my calculator. So 15/4. Take the square root to solve for h, okay? We're only going to keep the positive square root because h can't be negative, okay? So we get that h equals, oh my gosh, I'm so sorry, guys. This is going to take a step back here. Right? 4x squared minus 1/4 x squared is 15/4 x squared. Okay. Now we can take the square root, keep only the positive one. We get h equals, this simplifies, we have a root 15 over 2, and then x right here. So x root 15 over 2 is going to be our h. Okay, so up here, erase this, right? H equals x times root 15 over 2. And now we have everything we need to plug into our area formula, okay? So the area as a function of x is going to be 1/2 times our base, which is x, times x root 15 over 2, which simplifies with our algebra to x squared, right? X times x is x squared, and then 1/2 times root 15 over 2 is root 15 over 4, okay? Final answer. All right. So there's that, okay? All right. Let's move on to 18 here. Let's move on to 18, okay? Square is inscribed in a circle. Write the area of the square as a function of the radius of the circle. Okay, this isn't too bad. So a square is inscribed. Square is inscribed inside a circle. That means the circle passes through the corners of the square. Is what that means. Okay. Then we're going to draw the radius of this circle, but we're going to draw it in a strategic location, okay? We're going to draw the radius of our circle such that it intersects the circle at the corner of the square. At the corner of the square. And we're just going to say that that's R. So we want the area of the square. All right, that's going to be area of the square. If our square has side of length s, that means the area is going to be s squared. So we got to relate our s to our r somehow, okay? All right, so let's think about this, okay? I'm going to draw another radius here. Okay. Oh, what's going on? What's this? Is this like a straight edge or something? What is this? Oh my gosh. How do I make this go away? I'm just gonna, okay. Just push it off to the side, okay. Sorry about that. All right, so we have a radius right here. We have another S right here. So let's zoom in on just that little isosceles triangle. We have R here, and an S here. Okay, so we got to relate those two somehow, okay? All right. So one more thing we need to notice is the height of this isosceles triangle, okay? So looking back over here at our square, okay? We draw this height here, right? Notice that two of our heights equal two of these heights equal the length of the side of our triangle, the length of the side of our square. Two of our heights here are the same as the length of our one side of our square. So one height right here, the height of our triangle here is going to be equal to 1/2 s. Okay, I have a right triangle right here. So let's just focus in on one of these right triangles. Okay, I'll do this in, let's do orange. Okay. All right, so we got to relate R to S. We want to write S in terms of R and then plug it into our area equation right there, okay? So we can relate S and R with the Pythagorean theorem. So 1/2 S squared plus S squared equals R squared. Then we're going to solve for S, okay? So we get 1/4 s squared plus s squared equals r squared. 1/4 plus 1, I'm pretty sure is equal to 5/4, which it is. Okay, good. So it's going to be 5/4 s squared equals r squared. Get rid of this 5/4 by multiplying both sides by 4/5. We get s squared equals 4/5 r squared, okay? Then we just got to take the square root of both sides. We keep only the positive square root because the length of the side of our square can't be negative. So we have s equals 2/5 r. All right, let's rationalize that denominator. We get 2√5/5 r. Oh, no. All right, 2√5/5 r. Okay. So here, right, we have s equals 2√5/5 r. We can plug that in to our f for s up here. We get that the area equals 2√5/5 r, all that squared, because we want our side squared. That gives us 4 times 5 times r squared over 25, which equals 20r squared over 25, which equals 4/5 r squared. Okay, 4/5 r squared is going to be the final answer. So a of r as a function of r is equal to 4/5 r squared. So the area of our square is going to be 4/5 times the square of the radius of our circle here, okay? Let me get some water. All right. So, number 18 in the books, okay? So I'm going to get rid of some of this, okay? So just pause and go back over this if you need to. I'm going to get rid of this. So we can do 19. Let's look at 19. A sphere is contained in a cube tangent to all 6 faces. Find the surface area of the cube as a function of the radius of the sphere. Okay, sphere is contained in a cube tangent to all 6 faces. Find the surface area of the cube as a function of the radius of the sphere. Oh, fun. So I know how to do this one. I'm not good at drawing in 3D, so I'm going to try to figure out how to draw this thing. Okay, so we have a cube. So I'm going to start by drawing 2 squares, then connect them with parallel lines. All right. I'm not very good at things that don't have rules. I'm really good at things that have rules, but I'm not good at things that don't have rules. And art doesn't really have rules, so I'm not good at it. All right. But math has rules. Pretty good at math. All right, there we go. So there's a cube. Okay, there's a cube. All right, and then our sphere inside of it is going to be tangent to all 6 faces. What that means is our sphere is going to be inside of our cube, and it's going to fit just inside of it, perfectly inside of it, such that the sides of my sphere all barely touch the middle of each side of my cube, okay? So let me try to draw that in pink. Okay. I guess that's kind of acceptable. I don't know. Sorry, guys. It's probably not a $16,000 drawing, so please apologize to your parents for me. All right. So it's barely intersects, barely touches the sphere barely touches the 6 sides of my cube. Okay. All right. So I'm going to draw the center of the cube and the sphere, they have the same center in green. Okay. All right. And we want to write the area of the sphere as a function of the radius of the circle. So the radius, or no, a function, surface area of the cube is a function of the radius of the sphere. So we're going to draw the sphere, the radius of the sphere goes from this black point in the center of the top to the middle, to the center point. Okay, that's going to be R. Okay, it's going to be R. Okay, right, what do they want? Looking at number 19, they want the surface area of the cube, okay? What's the surface area of the cube? Okay, so the side, one side of our cube, it has length S. If it has length S, then the surface area is going to be, okay, it's going to be the area of one of our 6 faces, so that's going to be S squared times, and then there's 6 faces times 6. So surface area equals the area of one face, which is S times S, right? This is a cube. So the area of one face is going to be S times S, and then if we have 6 faces, the surface area of the entire cube is going to be the surface area of our 6 faces added up. So that's going to be S squared plus 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 S squared, or just 6S squared. So it's the surface area of our cube, okay? And we got it. What we got to do here is relate the side of our cube, or the edge of our cube, to the radius of the circle, okay? I think that's what we got to do. It's actually not too bad, all right? So let's think about this. Find the surface area of the cube as a function of the radius of the sphere. We just need to, it looks scary, but we just need to relate the side of our cube to the radius of our sphere, okay? Here's how we do that. So I'm going to go ahead and draw another radius from the center to the bottom, okay? So that's also R, okay? And I'm going to notice, okay? So I'm going to label this vertical edge here S, because that also has length S. We're going to notice and wonder, okay? We're going to notice that my 2 radii here stacked on top of each other equals the same length as the vertical height of the cube, which is equal to the length of one of the cube's edges, okay? So S, right, I guess another way of looking at this, we look at this from more like from the front. It's like more of a front view, right? So we have an R here and an R here. All right, so we notice that S equals R plus R, which equals 2R, okay? And then all we got to do is take this 2R, plug it in for S up here, okay? So we get the surface area is equal to 6 times 2R in parentheses squared, which equals 6 times 4R squared, which equals 36R squared. So surface area as a function of R, SAR, the surface area of R is going to be equal to 36R squared, okay? Remember the R in parentheses here, that's not a times R, that's saying like, that's telling my reader, okay, here's the surface area formula for our surface area, but it depends on what R is. So if we change R around, our surface area is going to change. It just shows that R is our independent variable and surface area is our dependent variable, okay? It just says that they vary, okay? So I'm just going to go ahead and move this up. I got a little more space here. So screenshot, do whatever you need, okay? Number 20, let's move on to number 20. An isosceles triangle has its base along the x-axis with one base vertex at the origin and its vertex in the first quadrant on the graph of y equals 6 minus x squared. Damn. Or darn, sorry. Write the area of the triangle as a function of the length of the base. All right. Write the area of the triangle as a function of the length of the base. So let's think about this. What would this look like? So we're going to have, let's draw our axes first. So this is number 20. This is number 20. I want to make that real clear. Number 20. Let's draw our axes. Okay. And it says its base is along the x-axis. So we got our x-axis here. Okay, one base vertex at the origin, and its vertex in the first quadrant on the graph of y equals 6 minus x squared. So let's draw the graph of 6 minus x squared, okay? I'm going to use the dashed line for this. All right, do I like that? Yeah, I do, okay. So 6 minus x squared, okay? If you graph that, you can graph that. So I know I can do that. Hopefully a lot of you can do that just immediately in your head. But if you can't, just look it on your graphing calculator real quick. It's this little parabola here. Let's do a little zoom standard. All right. It's just a little parabola. And they just want the first quadrant. They just want the part that's in the first quadrant. So we just got to draw this little arc right here, okay? Notice that we're going to want to label these 2 points to actually have some bearing on, like, a length. Okay. So this looks like our y-intercept here. What's our y-intercept? Let's do trace. 0 y-intercept in the bottom left is going to be 0, 6. So let's draw that. Y-intercept is 0, 6. X-intercept, right, that's going to be equal to one of the zeros of my parabola. Okay, so we have y. So let's say 0 equals 6 minus x squared, or 0 equals 6 plus, or sorry, it's going to be, or 0 equals root 6 plus x times root 6 minus x. I just did difference of squares here. Ask Mr. Miller if you're having trouble seeing how I went from here to here. That's difference of squares, okay? And then, so my 2 zeros are x equals negative root 6 and x equals positive root 6, okay? So this point right here, this intersection with the x-axis in the first quadrant, since x is positive in the first quadrant, we're going to take this one, x equals positive root 6. So this is going to be root 6, 0, okay? Then what does it say? Now we can draw in our triangle with all its vertices, okay? It says the base along the x-axis, one base vertex at the origin. All right. And then its other vertex. I think I interpret this as the other vertex is in the first quadrant on the graph of y. Its vertex. I think the other base vertex is here, maybe. And then the other one's up there. Let me go look at the Miss White's solution real quick, see if she did this one. All right, let's go to page 160. Sorry for the delay, guys. Just having trouble interpreting that. All right. All right, well, I don't see on Miss White's notes key, so I'm just going to interpret this my own way. I feel like what's going on here is we're going to have the base. I think the base is like this. Okay, let me get rid of this orange dot. The base is like that. Okay, so this is going to be this point in the middle. Oh gosh, didn't want to do that. This point in the middle here is going to be half of this x. So let me move this. Okay, so this point in the middle here is going to be root 6 over 2 because it's half the distance from the origin, right? It's right in between root 6 and 0, 0. Okay, so then this height here, the height here would be the same as calculating the y value for when we plug. So our function they give us is y equals 6 minus x squared. So this height here is going to be the y coordinate for when we plug root 6 over 2 into our function. Okay, so that's going to be, the height's going to be y. Let's do h. The height's going to be 6 minus root 6 over 2 squared, which equals 6 minus 6 over 4. Okay, 6 minus 6 over 4. Let me do it on my calculator real quick because it's 5:30 and my brain is fried. Oh no, I gotta finish this one, guys. I'm so sorry. All right, bear with me. 6 minus 6 over 4. That's 9 halves. All right. H equals 9 halves. Okay. So that height is equal to 9 halves. Okay, and then we got, if you notice, we draw these two lines in. That gives us an isosceles triangle. All right. So they want to know, right, the area of the triangle. Area of this triangle, right, as a function of the length of the base. All right, well, the length of the base is root 6, isn't it? The base has a length of root. So let's zoom out on this triangle. Okay. Origin over here to root 6 is going to be length of root 6. And then our height is what we find, 9 halves. Height is 9 halves. So then the area is going to be 1/2 base times height. It's going to be 1/2 times root 6 times 9 halves, which is going to be 9 root 6 over 4. That's what I got for the area. That's not a function, right? That's just a constant. So I'm not sure what's going on here. I think I just interpreted this wrong. Just go ahead, if you're confused, maybe ask Miss White or Mrs. Ford, but go ahead, stop right here, and since we didn't get through 1.7, just spend the rest of the time trying to just like go back over this stuff. Ask Mr. Miller questions if you need to, okay? But no, we'll just make sure you get the 1.6 homework squared away with Mr. Miller, that you understand everything, because that's going to be on the quiz tomorrow. So you go ahead and just ask and study for the quiz, okay? Look over your basic family of functions. Take care, guys. So that you're watching this Thursday. So for tomorrow, you're going to have your quiz. Don't do the 1.7 homework for tomorrow. We'll get through that. We'll get through the rest of this tomorrow after the quiz, okay? So just go ahead and watch just go ahead and study for the quiz tomorrow. Make sure you understand the 1.6 homework, and then we'll pick back up with this tomorrow after the quiz. Take care, guys. Bye.